vector bundle over our Twistor space, and this holomorphic vector bundle encoded the information of a self-dual gauge field on complexified Minkowski spacetime. And a kind of practical way of thinking about this was that this vector bundle was equipped with this partial connection, big D bar, which we can think of as little d bar locally plus A, where A is some you can think of it as a connection 1 form. And this thing had to be holomorphic, so it had to square to 0. And this implied the existence, at least generically, of a holomorphic frame for the vector bundle x lambda lambda bar, which took the vector bundle over any Twistor line and sent it to Cn, and it obeyed d bar. The partial, it was annihilated by the partial connection restricted to any Twistor line. So now, today, I'd like to try and take some of the facts that we've learned and actually tell you something that's of some incredible scenes. Of some sort of direct relevance to celestial holography. Nothing I've told you so far has been of, shall we say, direct, has directly connected with anything Sabrina has told us, but hopefully by the end of this lecture we'll have said something that's at least getting in that neighborhood. But first I'd like to start with a sort of different sounding question, which might not seem like it's going anywhere in particular, which is just this equation. Can we realize it as a classical equation of motion? That is to say, is there some classical field theory, if you like, that I can write down that has this kind of defining equation for the holomorphic frame, the holomorphic trivialization of this vector bundle that encodes self-dual Yang-Mills theories? Can I get this defining relation just as the equation of motion of some action functional? And the answer is yes, or it would be a short lecture. So these action functionals are often called Twistor sigma models or chiral sigma models. They exist for a variety of theories that have descriptions in terms of Twistor theory. I'm going to show you the one for self-dual Yang-Mills theory. Okay, so today let's fix a gauge group. Say SUN. And let's consider some fermions let's call them alpha I x lambda lambda bar beta I of x lambda lambda bar living on CP1, so on Twistor lines. And here I, upstairs and downstairs, are just fundamental and anti-fundamental indices of SUN. So this just goes from 1 up to n. And now we're just going to take the following action. This thing is a functional, if you like, of the partial connection. Take an integral over CP1. Let me write the expression and then I'll explain my notation. So Okay, so this capital D lambda is just shorthand for lambda alpha d lambda alpha contracted using our usual SL2 invariant inner product. This is a 1-0 form on CP1. So it's on CP1 because it only depends on the lambdas. It's a 1-0 form because I have d lambda. There's no lambda bar anywhere. And it's weight 2, homogeneous of weight degree 2 because there's 2 lambdas in it. Okay, so for the mathematicians in the room, this is the thing that trivializes the canonical bundle of the Riemann sphere. Now, what I've written right now doesn't actually make projective sense because this has scaling weight plus 2, but this doesn't have any scaling weight. So to get an action functional that actually makes sense, I have to break explicit Möbius invariance and just pick a couple of points on the Riemann sphere. Let me call them omicron and iota. There's a way of setting up everything I'm telling you that doesn't require you to make these choices, but I just like to be as explicit as possible today. So this is our action functional. It depends on the partial connection d bar, and its equations of motion are just that each of these fermions is holomorphic. Okay. So then, if we define our holomorphic frame, so remember this guy is matrix valued. So let's call it ij. Then on the support of the equations of motion of this action, we have that d bar restricted to x of h is equal to 0. So my claim is that this very simple 2D CFT has as its equations of motion this defining feature of the holomorphic trivialization of the Ward bundle on Twistor space. So this action, if you like, it governs holomorphic maps from CP1 into the Lie algebra of SUN. And this is what we mean when we say that it's a chiral sigma model, or Twistor sigma model. Now, if anyone here knows anything about string theory, and you've learned about heterotic strings, you might recognize sort of the features here as being how you cook up a worldsheet current algebra for SUN in terms of free fermions. So in some sense, that's all that's happening here, but rather than as a quantum mechanical 2D CFT, we're just thinking of this in completely classical terms right now. Yes?
So alpha is the equation motion of alpha. Liba alpha is permitted the distributional support on the poles.
Okay, so for this to make sense, there's some boundary conditions on alpha and beta that they vanish at first order at the points omicron and iota. Yeah, exactly. So one way I could get rid of having to lug this condition around with me is to cover up all of this and say that each of these guys is a section of the holomorphic spinor bundle. That would be the covariant way of doing things. Okay, so positive helicity gluons, these are just perturbations of the self-dual sector of Yang-Mills theory. So in some sense, we should be able to get something that represents a positive helicity gluon by just considering a perturbation of this action around a trivial gauge field. So if we think of d bar as being the flat, the trivial partial connection, plus some perturbation A, which I now think of as small, so a kind of infinitesimal perturbation. Then, as we saw yesterday while discussing the twisted photon construction, then the condition that d bar squared is equal to 0, big D bar squared is equal to 0, is just that this little a is equal to 0. So I can think of this a as just being in H01, PT, curly O. But now I allow it to be in the Lie algebra of the gauge group, which today we said was SUN, so let's keep our notation consistent. So yesterday when we did the twisted photon, we didn't have this Lie algebra bit there. We just said it was an abelian gauge field. Here I'm thinking this as a linearized non-abelian gauge field. So that's why I still get the just usual cohomology condition, but it takes values in the Lie algebra of the gauge group. And the reason why this is the Lie algebra of the gauge group and not the endomorphisms of the Ward bundle is because when this guy is linearized, those endomorphisms are just the Lie algebra of the gauge group. So the vector bundle has a kind of trivial structure on Twistor space. So then if we take the Twistor sigma model evaluated on d bar plus little a, what we get is just the Twistor sigma model, which will give trivial holomorphic frames, plus something I'll call V, where this V is equal to an integral d lambda, omicron lambda, iota lambda, let's say alpha I, A, I, J, beta J, where this A is pulled back to the Twistor line, again using the incidence relations as ever. So I can be a bit more explicit here if I take we'll just let the Lie algebra valued index be free. So we can say, let's let A be equal to TA I J A, what shall I call this? Let's call it A plus. So I write everything here in terms of generators of the Lie algebra of SUN. So A here goes from 1 up to n squared minus 1. These are adjoint indices. And define JA of lambda as d lambda over omicron lambda, iota lambda, alpha I, beta j, TA ij. Then I can rewrite this object V, which now I'll make explicit the adjoint index on it, as an integral over CP1 JA of lambda, which A plus restricted to X. So if anyone has ever seen gluon vertex operators in the heterotic string, they look more or less exactly like this, except instead of a Twistor wave function here, you have something that you construct in terms of some world sheet fermions. Okay, so now let's see what this vertex operator actually looks like for the conformal primary wave functions that Sabrina showed you all yesterday afternoon. So first, we'll write down what it is for a momentum eigenstate. So this is something that is covered in detail in the Jiminy Cricket in the lecture notes from yesterday that we didn't have time to do live, so to speak. So I'm just going to write down the following object, and I'll explain what all the ingredients are when I'm done writing. Okay, so here I have some on-shell 4 momentum, which is massless, so I can write it as a product of spinors of opposite chirality. If this were Lorentzian real, this would be the complex conjugate of this one, but we'll allow ourselves to live in the complex world. Iota, again, is just some constant reference spinor corresponding to some choice of a point on CP1. This object, delta bar, of any complex number, I define this to be 1 over 2 pi I times the d bar operator of 1 over that complex number. Now you might say, remember this d bar, this is dz bar, d by dz bar. You might say, well, this is a z, not a z bar, so surely that derivative is 0. But of course, because it's 1 over z, there's a pole. And so d bar picks up precisely that pole. And what you end up getting is you get a delta function in the real part of z, a delta function in the imaginary part of z, dz bar. So in particular, these objects that we write as delta bar of something, they really act like Dirac delta functions, but they carry some differential form weight. So in particular, if you have, say, some holomorphic function f of z, and you integrate it against delta bar of z, you get f of 0. So in the lecture notes from the last lecture, I prove this for you. So if you don't trust me, you can go and convince yourselves that it's correct. So what have we got here? My claim is that this object is a kind of positive helicity Twistor wave function. Okay, so in particular, this needs to be valued in H01 on Twistor space, homogeneous of degree 0. So let's check that. So first of all, let's check the homogeneity. So here I have one factor of lambda that's upstairs, but then I have this delta bar of the SL2 invariant contraction between lambda and kappa. Delta bar goes like d bar of 1 over its argument. So this thing has homogeneity -1, which cancels the homogeneity here. And then the argument of the exponential is homogeneous of degree 0 as well, because I have a mu upstairs and a lambda downstairs. So the whole thing is homogeneous of degree 0. It's a 0-1 form, because this delta bar is proportional to d bar of its argument. So to say it's a 0-1 form, a mathematician would murder you for saying this. It's a 0-1 distribution, but for our intents and purposes, it's a 0-1 form. And also you can show that it is d bar closed. So if I came and I hit this thing with a d bar on Twistor space, I'm not going to see this because it's in the numerator, so it's holomorphic. I'm not going to see this because this is going to be proportional to d bar squared, and d bar squares to 0. And you could worry that you'd maybe pick up a pole here from the d bar acting on the exponential, but that's going to be proportional to d lambda bar, right? This dude's already proportional to d lambda bar, and there's only one projective degree of freedom in lambda, right? Because on Twistor space, the two components of lambda alpha cannot be simultaneously vanishing. So that means that d lambda bar wedge d lambda bar is 0, so the whole thing is d bar closed. And it's also easy to argue that it's not d bar exact, it's not d bar of some function. So this thing really is an H01 PT curly O, and you can amuse yourselves by throwing it into a Penrose transform integral formula. You can do the integral explicitly against this delta function, and you'll get the zero rest mass field for a positive helicity photon. Okay, so leave that as an exercise. I ask you to take my word for it. And now, as Sabrina was telling us yesterday, the idea is that you get these conformal primary wave functions by doing Mellin transforms in the frequency of massless momentum eigenstates. Right, so how are we going to do this on Twistor space? So to do that, we break, or we fix the little group scaling of these SL2 spinners. We'll fix the little group scaling by taking kappa alpha to be equal to square root of the frequency z alpha and kappa twiddle alpha dot to be square root of the frequency z bar alpha dot. So I'm going to use bar on my z's here, but this is just a convention to make the formulae look like formulae you may recognize from papers that you've read in celestial holography. This does not need to be the complex conjugate of this z. It can be, but it doesn't need to be. Okay? So now here, where we now think of z alpha and z bar alpha dot as homogeneous coordinates on the celestial sphere, or the complexified celestial sphere. Which is, of course, just the Riemann sphere. So this is just another way of writing the statement we've heard many times this week, which is that a null vector in 4 dimensions is given by a scale, a frequency, and a point on the celestial sphere where it's pointing. Right? So frequency, the point. Okay? Some non-infinitesimal chalk. Okay, so under this parametrization, our positive helicity Twistor wave function looks like iota lambda over omega iota z delta bar lambda z. Okay, so all I've done here is I've used this rescaling along with the homogeneity properties of this delta bar guy. Okay? So now we can make some choices that will make our lives easier. You don't have to make these choices. You can carry around this whole thing, and then everything I tell you from now on will still work. The formulae will just be a bit clunkier. But I'm going to make my life as easy as possible. So we'll say we're going to simplify our lives. We're going to work on the patch of the celestial sphere where we can take z alpha to be 1z, z bar alpha dot to be 1 z bar. And we'll also choose iota alpha, this reference spinner we're carrying around, to be very simple. Just have the form 0, 1. Please.
Yeah, just to be sure, the argument of the A plus, so the capital Z is not.
Yeah, okay, sorry. Let's stop harming ourselves. Mu and lambda, those are the coordinates on Twistor space. Yeah, sorry. Yeah, somehow my capital Z's and my lowercase z's aren't so distinct. Yeah, that's right. So this, you should think of this as an object that lives on Twistor space. These little z's are just the parameterizing where the momentum is pointing. Okay, so with these choices, the contraction iota z is just equal to 1 on this patch of the celestial sphere. So we can stop carrying around these factors of iota z everywhere. So from now on, we're just going to use A plus is equal to iota lambda over omega delta bar lambda z exp I omega mu z bar iota lambda. Okay, so we haven't done anything sinister here. We've just gone to some local affine coordinates on the celestial sphere, made a nice gauge choice. These choices of constant spinners always boil down to some gauge choice on spacetime, some residual gauge freedom. So we just fixed that in a nice way that's compatible with the affine patch of the celestial sphere that we've gone to. Okay, so then the Mellin transform that Sabrina told us about yesterday. This is given by the integral from 0 to infinity d omega to the delta minus 1 of this guy A plus. So in real money, this is equal to the following integral. We now get a omega to the delta minus 2 coming from this 1 over omega here.
Shouldn't the denominator in the exponential also be equal to 1 in this calculation?
No, because I haven't gone to an affine patch of the Twistor spheres.
Oh, okay.
You could go to such a patch and it would be equal to 1. The reason why I'm not choosing to do that is because it obscures the scaling weight of this as a cohomology class on Twistor space. Going to this patch obscures the little group weight in terms of the kinematics on spacetime, but we trust we're going to try to be computing some kind of gauge invariant things, and everything should kind of come out in the wash there. You could do this. I'm just not doing it. Yeah, absolutely. Okay, so now you can just evaluate this integral. Go on Wikipedia, look up your tables of Mellin transforms. And what do you get? You get the following thing, minus I, 1 minus delta. You get a gamma function in delta minus 1. You get iota lambda to the delta. You get a delta bar of lambda z. And this is all over mu z bar to the delta minus 1. Now, again, you can amuse yourselves. Throw this now into those Penrose transform integral formulae we met in the second lecture, and you'll get the wave function, or rather the field strength of the wave functions that Sabrina wrote down for you yesterday on the nose. So these really are the Penrose transform representatives for positive helicity conformal primary gluons or photons. We can simplify this a little with some notation. If we let's define delta bar sub delta lambda z to be iota lambda to the delta plus 1 delta bar lambda z. And the kind of expression we'll have in mind here is the Twistor representative that I'll call A plus sub delta. And this dude is just minus I, the 1 minus delta, gamma delta minus 1, delta bar, delta minus 1, lambda z, all over mu z bar, delta minus 1. So this is a positive helicity conformal primary gluon on Twistor space, as represented on Twistor space by the Penrose transform. Now, you can take your favorite spin zero rest mass field on space-time in its momentum eigenstate representation. You can lift it up to Twistor space doing the exact same thing using the Penrose transform, and you can Mellin transform it in the exact same way. So we can write down these Twistor representatives for massless conformal primary wave functions on Twistor space for any spin. Okay? I'm showing you the one for positive helicity gluons just now. Okay, so now I want to go back to this expression we had up here. It's kind of like a vertex operator, an infinitesimal deformation of the self-dual sector according to this Twistor sigma model we have. So the corresponding vertex operator in the Twistor sigma model is something we can call VA delta, which is just the integral over CP1, this current JA of lambda A plus delta, pulled back to the Twistor line. Okay, so now you've probably no doubt noticed something about the functional form of this that Tom has certainly told us about and that Sabrina alluded to yesterday evening, which is that it has poles whenever the argument of this delta function is a negative integer. All right, so the wave function, and hence the vertex operator, has simple poles whenever this scaling weight delta is equal, say, to some k, which is an integer less than or equal to 1. Okay? So in other words, the expressions don't make sense when k takes those values. So how do we get around this? Well, we just make a prescription for what to do with these objects when k takes these special negative, well, they're not quite negative, but integer values that are less than or equal to 1. So at such a delta, we define RKA of Z and Z bar. We just define this to be the residue where delta is equal to k of the vertex operator for generic delta. And so it's a straightforward calculation to show what this is. What you get, integral over CP1, I to the 1 minus k, JA of lambda, mu z bar, the 1 minus k, delta bar, k minus 1, lambda z. There's a factorial here. And in fact, you can rewrite this. So remember these delta bars, they're things that essentially, when you do the integral over CP1, it's evaluating the rest of the integrand where the argument of the delta bar is equal to 0. So you can rewrite this just using Cauchy's theorem as a residue. So this is just equal to I to the 1 minus k over 2 pi I into 1 minus k factorial. And then you take a contour integral, JA lambda mu z bar 1 minus k iota lambda to the k. And this contour is just encircling the pole where lambda, where the SL2 invariant inner product of lambda and z vanishes. So if you like, so you can take it as a small circle around where the denominator vanishes. These two expressions are equal. Okay. So now you can do some kind of clever reshuffling of things. Let's relabel k is equal to 3 minus 2p for 2p minus 2, a positive integer, or rather a non-negative integer. So you can just show that this restriction on p is the same as this restriction on k. And use the fact that on the affine patch of the celestial sphere parametrizing the null momentum that we started out with, this spinor contraction of mu and z bar, this is just equal to mu 0 dot plus z bar, the affine anti-holomorphic coordinate, mu 1 dot. And then we can binomially expand this object RKA in Z bar. So what do we get? We get R to the 3 minus 2p A Z and Z bar is equal to a sum m going from 1 minus p to p minus 1. Z bar to the p minus m minus 1. Some modes, which we'll label by S, p comma a sub m. They depend on z still. And then this is over some gamma functions in p minus m, gamma function p plus m, for S p a m z. Okay, so all this is doing is rewriting these kind of effective vertex operators we're defining for when delta takes these special integer values in terms of some other modes that we're calling S. And now, the thing that's cool is that somehow we can ask what happens when these modes talk to each other. So we can say we want to compute say the commutator SPA M with SQB of N. So how do we do this? Well, the point is that we're trying to do this computation within the confines of some linearized perturbations within the self-dual sector of Yang-Mills theory. These things are governed by the Twistor sigma model that we wrote down before. So you can define what you mean by this commutator as just the classical contraction between these guys, SP, say this one is evaluated at Z and this one at Z prime. And the Twistor sigma model. So what do I mean by classical contraction? Generally, if you have a quantum 2D CFT, you have two operators in that CFT. You want to compute what happens when they get close to each other. You have to take all the Wick contractions you can possibly take between these operators. This is what you would do in string theory, for instance. But here, remember, this Twistor sigma model for us is just a classical field theory. So that means we only allow single Wick contractions when vertex operators get close to each other. Okay? So rather than doing the calculation, I'll give you the tools to do it and tell you what the final result is. So from the Twistor sigma model, you can show that the classical contraction between two of these currents, say at lambda and lambda prime. So when I say classical, what I really mean is single Wick contraction. This is equal to d lambda f a b c j c lambda prime lambda prime iota lambda prime. Okay? And what this means is that all of the action in computing the Wick contraction of this dude with this dude is coming from the Wick contractions of the two currents, JA with JB. What you find, remarkably, so you turn the crank. I'll say more what I mean by that. And you find something remarkably simple. You find that these modes S form an algebra, in particular a Kac-Moody algebra of level 0. Now, this level condition one shouldn't take too seriously because we were treating these things classically anyway. generically in Kac-Moody algebras, the level emerges as a quantum mechanical effect coming from multiple Wick contractions. So you probably really shouldn't take this too seriously. Now it's the what is it a Kac-Moody algebra of? Let's look at what these S's are built out of. So there's some business in the denominator that's basically just making up weights and telling us where to take this contour integral. But what's in the numerator are components of the Twistor variable mu alpha dot to some power. So the numerator of these dudes are made up of bases of polynomials in C2, right? The ranges of these indices, P and M, ensure that these are always positive, or rather always non-negative powers of mu alpha dot. So we're getting maps from C2 into the Lie algebra of the gauge group. So this is really the Kac-Moody algebra of maps from C2 into SUN. And in fact, there's more than this lurking here, because you can always do some formal Laurent expansion in Z. So you can formally expand and let's just write down what these are. Okay, so if you now go to an affine patch of the Twistor sphere, you can write this as in this somewhat more enlightening form. And here, this complex number lambda is just playing the role of a complexified loop parameter. So what you're actually getting, let me come back over here to summarize. You find is that the set of these modes, P, A, M, R, form the loop algebra of the Lie algebra of the gauge group, the Lie algebra valued polynomial maps from C2 into the Lie algebra. This thing is also sometimes called the S algebra. And in particular, in the context of celestial holography, this is the thing that was discovered as the algebra of conformally soft positive helicity gluons. In Twistor space, you get it this way, as infinitesimal deformations away from the self-dual sector. And in fact, this Lie algebra is precisely the thing that preserves all of the conditions that are in Ward's theorem. So even if you didn't know anything about momentum eigenstates and Mellin transforms, if you knew Twistor theory, if you knew the Ward correspondence, someone came up with you with a gun and said, tell me what are the things that are going to infinitesimally deform the Ward correspondence, this is what you would write down. In 1977, this is what you would have written down. So somehow celestial holography is rediscovering this fact using explicit studies of scattering amplitudes, but it's something that twistor theory gives you very naturally. And I haven't told you anything about gravity, but in fact, there's a story for gravity for every single lecture that I've given you this week. There's an analogous story you could give in gravity, and there you would also find some infinite dimensional Lie algebra associated with infinitesimal deformations of the self-dual sector of gravity. So I think in the interest of us eating, I will stop there. Thanks. Go forth and eat.